Hello there, algebra. Sorry, hello there, algebra students. Um, sorry I can't be with you live today, but that's just sometimes how things work. Everybody is safe. I'm fine. This is not a COVID thing. I just needed to be home with my kids today. All right, so we're going to do the same lesson that we would have done live, except for you're sitting in your desks like normal, and I am not. But you need to get a graphing calculator. If you need to borrow one, go grab one now. If you have your own, get it out and turn it on. Pause the video. I'll wait for you. Actually, no, I'm not going to wait for you. Pause the video, then when you're ready, restart. So what we are going to do is focus on our absolute value graph. And as we use the absolute value graph to see how putting different numbers with the parent function, we're going to experiment with those numbers and see how the graph changes and how it moves. So the first thing you need to do, one, is remember that you can pause this video whenever you want. If I'm going too fast, if you need time to make the graphs, make sure you pause the video and go at your pace. You do not have to go at my pace. All right? So you should have your blue notes packet out, lesson 2. And the first thing we're going to do is graph the basic parent function like we did yesterday. F of x equals the absolute value of x. That was a graph that had the vertex right at 0, 0, and both sides increased by a slope of 1. So up 1 over 1, 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 up 1 over 1. So it went right through the corners of the graph paper and made a perfect V shape. Absolute value makes a V-shaped graph. So in the left side of the graph, it will still go up 1, left 1, 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 going backwards. So that it makes a nice perfect V shape. We're going to label that f of x, and that is the absolute value of x. Now what we're going to do today is use the graphing calculator instead of Desmos. I'm going to show you how to use the graphing calculator to help you with these graphs. When you're home over the weekend working on the blue packet that the sub is supposed to hand out to you, you can use either Desmos or the calculator, whichever one you like better or have access to. Okay, so make sure your calculators are ready. So here's what we're going to do next. We are going to look at the graph f of x equals x plus 5. Notice that the plus 5 is after the absolute value symbol on the outside of the absolute value bars. So we're going to go over to our calculator, turn your calculator on. We are going to push the calculator button on the left-hand side. You can see my little circle swirling over it. Now we're going to push that and you should get a graph. Couple things. I'm trying to troubleshoot for you here. If there are graphs already on your page, you're going to push menu. See the red button? Menu. You're going to go option 1, so you can just push 1, and you're going to do option 4, which will delete all the graphs that are already there, and push enter. And that should get rid of any graphs that are there. Next, in order to enter your equation, you're going to hit the tab button, and you should have f of 1 pop up. If for some reason your calculator says something different other than f of 1, to fix it, you're going to go to menu, then option 3, graph entry edit, and then make sure you choose option 1, function, and that'll make this an f of x. So once that's taken care of, what we have to type in is the absolute value of x and then a plus 5 afterwards. So just like we did on Desmos, to get absolute value, you type in A, B, S for absolute value, then parentheses, x, and then after that you'll put plus 5. And then when you hit enter, you have your graph drawn. If your window is all funky and all weird, like you don't have the graph seen or the numbers are too big or too small, you can again go to menu, go to option 4, Windows or Zoom, and then you can go to standard, Zoom 5 standard. Okay, and notice that puts 10 in each direction on your window, or at least 10 in the x's. Another option is if you notice when you get your hand close to the axes, your cursor close to the axes, it turns into a hand. If you click on that, you can grab it. Notice how my hand closed, you can grab the axes. Anyways, you can grab the axes and zoom in and zoom out that way. The table of values on the calculator is found by doing Control T, puts the table next to your graph. Control T gets the table out of the way. Control T puts the table there. Control T removes the table. Control T brings the table back. Control T gets the table away. Control T, and then we can also just slide up and down with your cursor going up the table or down the table, whatever you may need. That'll give you dots to plot so you know what your graph looks like. But Control T moves the table out of the way. So what I'm going to do is I'm going to go back to tab, and I want to compare my absolute value graph from yesterday, absolute value of x, absolute value of x. I want to compare it with what we just graphed. So the red one that you see on my screen is our generic absolute value graph that we already put on our paper, and the blue one is the new one. So what we want to do is compare where they are located. So what we're seeing here on my screen is the sides increase by the same slant, so that means they are parallel. So they're going to have the same slope, so I can count the boxes the same way. But notice that the tip of the V has been moved up 5 spots. So now when I go back to our notes, the new graph takes the V, the turning point of our shape, or sometimes called the vertex, moves it up 5 spots. But the sides, left and right, will increase by the same rate. So it'd still go up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1 in both directions. Up 1, left 1, up 1, left 1, up 1, left 1, up 1, left 1. So that one is now our g of x. And the change in the graph, it shifted up 5 units. And what created that shift was the plus 5 that was at the end of the equation. So that plus 5 moved our graph up 5 units, and then all points. Technically what happens here, guys, is every point on this graph got moved up 5 units to create the next point. All right, so everything just gets shifted up 5. And that's exactly what happened in the table. All the points would be 5 greater. The y values are 5 greater than the originals. But knowing this plus 5, what happens to it makes it easier to graph, because if you know the patterns of how the numbers change the parent function, you don't have to use the calculator as much, because you'll know how to change the graph and just where to redraw it. All right, so let's look at the next one here. H of x equals x minus 9. So what do you think is going to happen with this graph? Where do you think it's going to go? If the plus 5 moved it up 5, what do you think is going to happen with a minus 9? Well, go to your calculator, hit tab, hit tab, and then type in absolute value A, B, S of x, and then afterwards subtract 9. So you're going to do ABS subtract 9, and then, okay, things are going funky. Of course they are. When we hit enter, the new graph down here, you can see, shifted our graph down 9 units down the y-axis. So if that's kind of what you were guessing what would happen, congratulations, you were right. So now over here, the vertex, the V point of our graph is going to be down 1, 2, 3, 4, 5, 6, 7, 8, 9 spots. And technically what happens is every point on the original graph gets shifted down 9 units. And the same pattern will happen with the slopes of the sides because everything was moved in the same direction, the same amount of distance. So that's called a translation. But you'll do more of that in geometry next year. Right now, what I want you to realize is that this minus 9 at the end of the graph, outside the absolute value bars, will shift the graph down 9 units. Now it goes down because it's subtraction. Kind of makes sense, I guess, that way. So the minus 9 that's here moved it down 9 units. The plus 5 moved it up, minus 9 moved it down. Okay, now what we're going to do is look at the next possibility and, oops, wrong page. There we go. And figure out what happens when we take our parent function and then do some work inside the absolute value bars. And we're going to compare how those move. So let's first draw our parent function. Remember, pause if you need to. If you need a second or two or a minute or two to catch up with your graphs, figure things out with the calculators. All right, so there's our f of x, or my f of x. You have to draw your own f of x. Now what we're going to do is go to the calculator and see what happens when I do x plus 4, where the plus 4 is going to be inside the parentheses. So when you go to your calculator and type in the absolute value, you're going to put x plus 4 inside the parentheses. So that's what you type in to your function on the calculator. If you need to, or if you would like to, what I'm going to do is hit Menu, Option 1, and Option 4, and that will get rid of all my old graphs. Then what I'm going to do is hit the Tab button, so I'm back to f of 1 of x. And then I'm going to put A, B, S, X. I'm going to graph the basic absolute value graph that we just put on our paper. That way I can see what happens with the new ones as I add in some other additional numbers. Once that graph is taken care of, I'm going to hit Tab. And then this time I'm going to do A, B, S, X plus 4 in the parentheses. So the absolute value of x plus 4 in the parentheses. And when I hit enter, boom, I can see that my graph moved again, but this time it went sideways to the left. And can you guess how much it moved? 1, 2, 3, 4 units to the left. So now that I know that the sides still increase by the same slant, so they have the same slope on both sides, I just take the vertex, the point of my graph, and move it to the left 4 spots, and then redraw it. So over here, the vertex was at 0, 0. I move it over 1, 2, 3, 4 spots, and then the sides increase by the same slope. Up 1 over 1, 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 and then up 1 left 1, up 1 left 1, up 1 left 1, up 1 left 1, up 1 left 1. That's our new graph. And the graph this time shifted left and went sideways 4 units. The left 4 units came from the plus 4 being inside the parentheses. So you might think that because it was a plus 4, it would go the other way, but this is backwards. When we go sideways, we're going to move in the opposite direction of our plus or minus sign. So the plus 4 actually moved to the left. It's kind of weird, but that's just the way it is. So what's your guess at what will happen on the next equation where we have absolute value of x minus 6 inside the absolute value bars? So I want you to think about it, what we just talked about and what we just did, how the plus 4 went to the left. Where do you think the minus 6 will go? And let's test it. So over here, I hit Tab to get a new function. And then I'm going to do absolute value, A, B, s of x minus 6. If I remember correctly, that's what it was. X minus 6, yes. Then I'm going to hit enter. And if you were guessing that it moved it to the right this time, 6 units, congratulations, you were correct. So now I'm going to go over and graph it by hand. So I'm taking my vertex, the turning point, and moving it over 1, 2, 3, 4, 5, 6 spots. The sides will increase by the same slope in both directions. So as I graph this, I'm still going up 1, left 1, up 1, over 1. And then that is now our h of x. So this one shifted right 6 units. And it goes right 6 units, oddly enough, because it was a minus 6 in the parentheses. So the sideways numbers go backwards from the plus minus part that's in the parentheses, or I'm sorry, in this case, in the absolute value bars. But if it's on the outside, it shifts up if it's positive, down if it's negative. So now we have to turn the page and figure out what happens with our basic absolute value function, which I'm going to graph real quick. There we go, my f of x. Now we're going to look at what happens when I take that basic absolute value function and put a negative in front of it. So on your calculator, you'll do a negative first, then the absolute value of x. And we're going to see what happens with our picture. Okay, so over to our calculator, I'm going to do menu 1, 4 and clear out my old graphs. Then I'm going to do tab absolute value of x. Oops. Wrong button. Tab absolute value of x. There's my parent function. Now I'm going to tab again and do negative first. So I'm going to do the negative sign first, then A, B, S for absolute value of x. Then let's see what happens with our graph. Bam! Look at that. The blue one was the original, the red one's the new one. So it looks like it turned upside down. That's what the negative does. It turns our graph upside down. So mathematically, the sides still follow the same pattern of counting boxes. Down 1, over 1, down 1, left 1. But we're going down this time. So we're going, flipping it upside down. So on my paper here, the vertex is going to be at the same point, but now I'm going down and down. So that's the new one. So how would we describe that? Well, it looks upside down, but mathematically what that means, it was reflected over the x-axis. Which means it was turned upside down. So that negative in front of our function turned our graph upside down. So now let's mix some of these things together. What's going to happen, do you think, when I do negative x, which flips it upside down, and then put a plus 2 after that? Based on what we did on the front page, what is that plus 2 going to do to our graph? Well, if you're not sure, what we can do is go over to our calculator and try it. So I hit the tab button, put the negative first, absolute value of x, close the parentheses, and then plus 2 after that. So now I have the negative absolute value of x and then plus 2 afterwards. So what's your guess as to what's going to happen with the red graph here? I know the negative makes it upside down like the red one, but what is the plus 2 going to do? If you said shift it up 2, then you are correct. So now we're going to graph that by hand over here. We're going to take our vertex, the turning point, move it up 2 spots, and then the sides will still have the same slope, and it will still be upside down like before. Oh, that was not very straight. So two things happened here. It was reflected over the x-axis, and the +2 at the end shifted it up 2 units. So we can have more than one change at a time. All right, I think we're coming up to the last option of what to do or how to change things, and that now is going to be through multiplication. So, just like all the other examples, I'm going to graph my parent function first. There are different parent functions because there are different families of functions. There's the absolute value, there's linear, quadratic, exponential, square root, cubic. Those are all different families because they all have different parents because they all have different looking graphs. Now we are going to take a look-see at what happens when I multiply times 2. All right, so why don't you take the moment to pause the video, go to your calculator, type in the function, and then let's see what happens. When you're done getting the graph, come back. So what you should type in is 2 and then ABSX, and then enter, and we get a graph that increases where the slopes of the sides now change. So it's going to increase faster. So the slope is more steep. So instead of going up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1, if we look at the table of values, Control T to see the table, we can see new points to plot on our graph as long as we are looking at function 2. So that's the function 2. Function 1 was the absolute value of x. That's the parent function. If I move my cursor to the drop-down menu and pick function 2, there's my 2 times the absolute value of x. Notice everything is twice as big, which makes sense because we multiplied it all times 2. So now the side lengths are going up twice as fast. So there are some points that'll help you plot your dots to make your graph. You could always move your cursor to get more points up and down the table. But now, to put it on our paper, what's happening here is we have the same vertex, but instead of going up 1 over 1, up 1 over 1, up 1 over 1, we are going up 2 over 1. So it's almost like that number that's in front of my absolute value bars changes the slope. It's now 2 over 1. Up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. So now my sides are increasing twice as steep as they were before. And same thing on the other side, up 2 over 1, up 2 over 1, up 2 left, up 2 to the left because we're going in the backwards. And there's our g of x this time. So the multiplication in front made our graph more steep. So the technical term is a vertical stretch. Of factor 2. The factor of 2 means I'm multiplying times 2. Vertical stretch would be like taking, if you were to take a graph, let's see if this works here, like click on it, and a vertical stretch would be, hang on, 1 second. Let me get a better picture to show you what would happen with this. Alright, so I need to use one of my own shapes. Okay, this will work. If I take a regular triangle, a vertical stretch would be if I pulled it down like this. Okay, a vertical stretch is taking your shape and pulling it vertically. It means pull up and down. And notice that it becomes more narrow so the sides become steeper. All right, so that's a stretch. I'm stretching it vertically, pulling at it up and down. So when that happens, when you pull on it up and down, what happens is the sides get steeper and the graph becomes more narrow. All right. So now the last thing we're going to graph and attempt to compare is a scale factor of 1/4. So we want to see what happens. We had 2, which is a number bigger than 1. Now we're going to test what happens when I use a number in between 0 and 1. So pause the video, go to your calculator and graph it, then come back and we'll compare. When you're trying to type this new function in, you can do 1 divided by 4 to get your 1/4, and then after the 1/4 is when you type in absolute value of x. So the 1 divided by 4 will give you the fraction of 1/4. And then we get something that looks like this. The slopes are less steep. It becomes more flat because instead of going up 1 over 1, up 1 over 1, up 1 over 1 like the original parent function, we're going up 1 over 4, up 1 over 4, up 1 over 4 for the new graph. So it's like that number 1/4 that's being multiplied times the absolute value changes the slope of our sides. So now I go up 1 over 4, up 1 over 4. And do that in both directions. So how would we describe this? Well, it becomes more flat. So this is a vertical compression. Of factor 1/4. What happens here is it makes the graph wider. Now if I go back to my triangle simulation up at the top here, what I'm looking at is the fact that this triangle, if it's stretched, it becomes more narrow. But if I take this and push on it, if I imagine pushing the top and bottom down, it's going to get flatter and wider. Okay, so the stretch, the narrow, will make it more narrow. But if I push on the top and bottom, like trying to squish a hamburger bun, it flattens out. So taking this original parent function, that was the one I used the black marker on, if I push down on it vertically, it's going to get it more flat, almost to the point where it might flatten out totally. So let's summarize everything that we just talked about in this lesson. Really, everything I talked about that you listened to and experimented with on your calculator in this lesson. So first, when we add or subtract a value outside the function, it either moves the graph up if it's positive, or it moves the graph down if it's negative. When we look at the plus or minus on the inside of the absolute value bars, it goes left if it's positive, or right if it's negative. And then if we put the negative in front of the whole function, it reflects the parent function over the x-axis. And lastly, what we just talked about, with a k multiplying, it'll either compress or stretch the parent function. The stretch makes it steeper or more narrow. The compression makes it wider or more flat. So that's everything with what we did in our lesson today. At this point, if your substitute teacher or whoever's there in the front of the room did not hand out the blue packet yet for you to work on over the weekend, you can raise your hand and ask for it from them. It should be a blue packet, and it is titled Lesson 2.5 and Lesson 2.75. So it's 2 days of work all in one packet. Technically, you have Saturday, Sunday, Monday, and Tuesday, 4 days, and there are 20 graphs to experiment with, and they're not all absolute value. We'll use some of the other families of functions as well to practice. So that's your assigned work for Monday and Tuesday, is to complete that blue packet. I'll expect it done when you come back on Thursday of next week. And then on Wednesday, there's a Delta Math assignment to work on. All right, so you can do those at whatever pace you want, as fast or as slow as you want, all in one day, or spread it out over a couple days. But expect to hand in that packet when you come back next Thursday. And then there's also a Delta Math assignment for you to do on Wednesday. All right, so good luck. Rewind and watch this as often as you need. And I hope you guys have a nice weekend. I'll see you next week.